Our next presenter is Andres Prada from the Illinois Sustainable Technology Center. Looks great.
Everyone. Thank you for the introduction, Sarah. So I have been working for the Illinois Sustainable Technology Center for over 3 years now. I'm happy to be here today and talk about this technique to destroy PFAS. So at this point, we are all familiar with PFAS, but how much can we find in our wastewater systems? So in the last couple of years, we have been working to sample the inputs and outputs of wastewater treatment plants in the state of Illinois. So we have been sampling landfill leachates, city sewage, the influence of the wastewater treatment plants, and then the outputs, effluent and biosolids. We use the EPA method 1633 that Jamin was explaining before. And then we measured for 14 types of PFAS. We found levels of thousands of parts per trillion, which means parts per billion at landfill leachates. And then city sewage influent hundreds of parts per trillion. And then at the outputs, we see that a lot of it's going to the biosolids. So we see again parts per billion range in biosolids. And then there can be some high effluents also in the and can touch the parts per billion level too, but mostly in the parts per trillion. So, but then how we actually treat them for PFAS? So we have to think like treating a small volume is less expensive than a high volume. So in the case of the landfill leachate, it's usually transported to the wastewater treatment plant from the landfill in semi-truck tankers of a maximum of 6,000 gallons. Whereas the influent for a small, medium-sized wastewater treatment plant is around 10,000 gallons per minute. So there is a huge difference between treating those two inputs. So there is one of the best available technologies right now. It's to remove PFAS from water is activated carbon. So very well known. So in its powder version, it can hold around 100 milligrams per gram. So if we think of treating a volume as like the tanker, 6,000 gallons, which is around 22,000 liters, and then we multiply by the concentration that we measure, the maximum, we see that in the tanker we can find 300 milligrams of PFAS. And in theory, we should be able to remove that with only 3 to 4 grams of activated carbon, which costs around $1, which is crazy. I know it's more complicated than that, but this is just an example of the amount of volume that we can treat with and the small amount of activated carbon that we will need. But then we have the contaminated activated carbon. Now the EPA in one of the latest reports lists 2 options to deal with the contaminated activated carbon. One is incineration, but there is now a lot of research showing like under high temperatures, the PFAS chain, the carbon fluorine chain actually breaks down into shorter chains or create other harmful components that can evaporate. And if we landfill it, we see that in the leachate, we can find again the PFAS. So that doesn't solve the problem, but there are some emerging technologies on the way. They are still under research and development, but those are listed also at the EPA and include pyrolysis, supercritical water oxidation, thermochemical oxidation, and mechanochemical degradation. So today we are going to talk only about mechanochemical degradation in the form of ball milling. So here on the left side, we see a ball mill, the one that we are using here. So it has some jars, and then inside the jars, there are some balls, stainless steel balls. So it spins the jars. So the collisions between the walls and the mix with a catalyst create so let's see. So the ball impacts create radicals from coming materials and localize high temperatures that mineralize the PFAS. So those collisions are able to break the carbon fluorine chain and mineralize the PFAS. So again, this is the one that we are using here. So it's officially called a planetary ball mill. So it has 4 stainless steel jars and inside the balls. And inside there is around 100 balls inside each jar. And it runs up to 600 RPM at ambient temperature, pressure, and humidity. And then we can treat solid materials containing PFAS and accompanied with commiling reagents or catalyst. So how it works, there is like a plate at the bottom that spins in one direction and the jars spin in the other direction. So one of the first studies that I found that used this technique was back in 2013, the destruction of PFOS and PFOA by ball milling. So they demonstrate that after 4 hours of treatment and using potassium hydroxide as the catalyst, they can destroy between 80 and 90% of PFOS and PFOA, and they demonstrated measuring the fluoride ion. But the problem with this is they need an insane amount of potassium hydroxide. So it's at a ratio of 40:1. So, and then later the EPA, in collaboration with some universities in New Zealand, so further tested ball milling. So in this case, they use no catalyst, but the consequence for that is you need to run it for a long time. So previously they demonstrated for 4 hours with potassium hydroxide. Now they had to run it for over 12 hours in quartz sun spike with AFFF. And then they demonstrated that it also work in soil impacted with these foams, but they have to run it for almost 24 hours to be able to reduce the concentrations. And they didn't measure the fluoride concentration, so they didn't demonstrate the actual destruction of the PFAS. Now, a more recent study is using piezoelectric materials. So the difference with the piezoelectric materials is with the balls collision, they create some voltage that it's also able to destroy the carbon fluorine bond. And then the dosage is way lower, so 5:1 compared with potassium hydroxide that was over 40. And then again, able to mineralize the PFAS in 2 to 4 hours. This is pure PFOS as an example, and then they also tested in sediment and measure the reduction of PFAS, of PFOS, or different types of PFOS, but didn't show the proof of mineralization. So we decided to to reproduce this technique here in our lab. So we bought the planetary ball mill, and then we started putting reproducing the same results. So we're putting pure PFOS and boron nitrate. So 100 milligrams of PFOS and 500 milligrams of boron nitrate, 5:1 ratio. And then at the beginning, we were finding similar results, about 90%. But then we decided to validate the method. So we put the same amounts in the 4 jars and ran it 3 times. And then we started getting a lot of variability, sometimes 90%, sometimes 0. So that's why we see here this long whisker and then an average of like 45. So quite different to the report, the scientific paper. So they don't specify how many times they run it, but this is what we find at 2 hours. And then at 4 hours, the results are more consistent. Whisker is getting shorter, and then with a average of defluorination of around 70–80%. And also we went ahead. This is just preliminary results. I will still be working on this during the summer. So far, what I did was absorb 100 milligrams of PFOS into 1 gram of activated carbon. So just filling up the activated carbon to the limit, and then ball milling that. So far I was able to validate it. So 3 times for 4 hours with 4 jars with the same concentration. So results are more consistent. I'm getting an average of 85% destruction, sometimes more, sometimes a little bit less. But yeah, but also in general, so the machine it cost over $4,000, but then to operate the system is really cheap. So powder activated carbon is around 25 cents per gram. Then boron nitrate is around $2 per gram. Energy very low, so 0.14 kilowatt hour per hour. So if we look at the rates in Illinois, it's around 10 to 12 cents per kilowatt hour. So we need 1.7 cents per hour to run the instrument. So for example, if we want to destroy 100 milligrams of PFOS, then we need 1 gram of activated carbon, so 25 cents. 500 milligrams of boron nitrate, $1. And then around 7 cents for energy, for a total of over $1 to operate this instrument. So if we remember, we need to destroy, ideally, in theory, 3 to 4 grams of PFOS if we want to treat a full tanker, in that as an example. So in summary, ball milling is one of the emerging techniques to destroy PFAS accepted by the US EPA. Requires no heat, no solvents. Catalysts definitely increase the effectiveness and efficiency of the technique, and piezoelectric materials are a promising catalyst. So far, boron nitrate works. My plan is to test other piezoelectric materials, find another one that can be more powerful than boron nitrate. So we can use ball mill in tandem with activated carbon to destroy PFAS in water, which is great. And the operational cost, for example, to destroy 100 milligrams of PFAS is just over $1. So I want to thank my team, my coworkers, John, Jamin, my student Julissa, and Lee, for the analytical work. And I can take any questions.
Great. Thank you, Andres. We do have one question so far.
Yep, I can go ahead and read that one. It says, is this a RCRA permitted treatment technique for PFAS chemicals?
That's a good question. I'm not sure. So I can look up, but it's not. So thank you, John.
Yeah, it is not, is the comment. I had a quick question about scalability. I'm not a chemist. I'm not that familiar with ball milling, but it seems
Mhm.
like we would be talking about, relatively small amounts of activated carbon.
Mhm.
But is it possible to scale this up? Like, can you make an enormous ball mill? I mean, obviously it would take more energy and more materials, but is that in theory something that's possible?
Yeah, but that's the thing. If, as I showed in the beginning, we can either treat the landfill leachate or the influent or the biosolids or the effluent. So if we are thinking about pounds of a material, so let's say we are talking about treating biosolids. So in that case, yeah, we need a huge ball mill or something. But if we are thinking to treat water, where usually the concentrations are very low, and then I'm putting the example of landfill leachate, which are way higher, then we can concentrate an enormous amount into a few grams. So that's kind of the way we envision the scaling of this system.
That makes a lot of sense.
Thank you.
Thanks, Andres.